Hello everyone, my name is Aishwarya,
And I'm Ellia.
and today we'll be presenting the physics behind magnetic resonance imaging, also known as the MRI.
So our learning objective today is that students will be able to understand the basic principles of an MRI machine and explain how they operate.
So, MRI machines are typically used in the hospital to form detailed images of the structure of a patient's blood vessels, nerves, bones, tissues, and organs. What they do is they scan several 2D layers of these concentrated areas and they put them together to create a multidimensional image. And these help doctors diagnose certain medical conditions without having to directly invade the body. The MRI machine is a complex device with several parts. However, for this video, we'll be focusing on the three main components: the radio frequency coil, the gradient coils, and the main magnet.
So, how do MRI machines allow us to see inside of us without cutting ourselves open? It has to do with the water content in our body. So humans are composed primarily of water, a polar molecule containing hydrogen atoms. These hydrogen atoms contain a solitary proton, which acts like a miniature magnet. And these protons have a quantum property called spin that enables them to align with external magnetic fields while remaining in place within the body. And the rate at which these protons spin is called their precession frequency.
MRIs operate based on the fact that we contain so much water. They produce a strong external magnetic field, which our hydrogen atoms become aligned with. The protons in these hydrogen atoms will precess, or spin, in alignment with the magnetic field at a resonant frequency. This alignment occurs along the longitudinal axis.
So this resonant frequency of the protons is determined by the Larmor equation. And according to this equation, the resonant frequency is proportional to the external magnetic field. Omega here is the precessional frequency of the proton, gamma is called the gyromagnetic ratio, and B is the strength of the external magnetic field.
Radio frequency, or RF pulses, are directed at the subject within the external magnetic field. These low-frequency pulses flip the protons in the hydrogen atoms out of alignment with the external magnetic field. Instead, they begin to precess in alignment with the transverse plane, which is a higher energy state.
So the strength and duration of these radio frequency pulses determine how much the protons become unaligned with the main magnetic field. What's called a 90-degree radio frequency pulse is what is needed to flip the protons into the transverse plane. Also, an RF pulse must be tuned to the precession frequency of the protons in order to alter their alignment. In other words, the RF pulse is in resonance with the precessional frequency of the protons.
Once the radio frequency signals stop, the protons relax back into alignment with the original magnetic field. They fall from a higher energy transverse plane down to the longitudinal plane again. When these protons relax to their original state, they fall out of alignment with the transverse magnetic field and emit an RF signal. This is a bit like how electrons fall down from an excited state to emit light, and that's essentially what's causing these images.
So the relaxation occurs in two phases called T1 and T2 relaxation. T1 time is the time that it takes for 63% of the protons to realign with the original longitudinal magnetic field. And T2 time is the time at which 37% of the transverse magnetization remains.
The RF pulses emitted by realigning the photons are the electromagnetic signals. They contain oscillating magnetic fields and therefore produce magnetic flux, according to Faraday's law of induction. As you may remember, this law says that a changing magnetic field induces an electric current. This current is induced in the receiver coils, which is how the signals from the realigning protons are detected and used to create an image.
So, what information do these radio frequency signals give to us? Since different parts of the body have different water content levels and unique compositions, in each tissue, the protons relax at different rates and produce distinct signals. Abnormalities and disease can increase water content and may be detected through unusual signals corresponding to heightened water concentrations. This is how MRI scans differentiate between different tissues. However, gradient coils are still needed to extract meaningful data from the sea of radio frequency signals emitted by the protons.
Gradient coils are used to determine the precise location of where the signals are emitted from through spatial encoding. They create magnetic field gradients that add or subtract from the main field. Gradients with varying strengths and orientations excite protons that are located only in a specific area or slice of a space, called the K-space. Higher gradients will induce a greater resonant frequency and a more rapid precession in the protons. By compiling all of the different K-spaces or slices of information where different signals are picked up from, a complete picture is formed, and this is done with the computer connected. Think of each gradient in K-space as a filter. Combining all the filters, or K-spaces, creates the whole image, which is what the MRI scan produces.
So, we saw that the radio frequency signals emitted by the realigning protons are detected with the receiver coils. The computer then digitizes the signals and applies a Fourier transformation. If you remember, we did this in AP Physics 1 to extract data from the frequencies that we measured in our instrument projects. The signals are then converted into meaningful cross-sectional images that tell us about the composition of our body at different locations and allow us to detect diseases and other problems within our body. So, to recap, an MRI machine generates a strong magnetic field which the protons in the water of our body align with.
This alignment is then disrupted with a low-frequency radio pulse, which causes the protons to flip out of alignment with the external magnetic field.
After the radio frequency pulses are turned off, the protons realign with the main magnetic field, which is a lower energy state, and emit radio frequency signals that are detected by the MRI machine.
Because different parts of our body contain different concentrations of water, the images produced by the emitted energy will accurately show where the healthy and damaged parts are.
Thank you for listening. Here's our works cited, and now we can take any questions.